Good afternoon. This is Kavipriya, Assistant Professor, EC Department, SMS College of Technology. I am going to deliver a topic called dielectric boundary condition from the subject electromagnetic fields. Practical electromagnetic problems often involve media with different physical properties. So determination of electric field for such problem require the knowledge of relations of field quantities at the interface between the two media. The condition that the fields must satisfy at the interface of two different media are referred to as the boundary conditions. So this is we're going to find the boundary condition for a perfect dielectric material. We have medium 1 and medium 2, and we have going to find the medium 1 is a dielectric material and medium 2 is a dielectric material. We are going to find the boundary condition for the boundary conditions for the in between medium 1 and medium 2. So we can express the electric field in terms of tangential and normal components. So electric field can be represented as, for example, E1 can be represented as E1t plus E1n. 1t is nothing but it is a tangential component of the medium 1, and 1n is nothing but it is a normal component of medium 1, electric field component. Similarly, E2 is nothing but E2t plus E2n. E2t is a tangential component of electric field of medium 2, and E2n is a normal component of the electric field of the medium 2. Around a small closed path, we get E tan 1 del W minus E tan 2 del W is equal to 0. So the small contribution to line integral by normal component of E along the sections of length del H becomes negligible as del H decreases and closed path crowds the surface. Immediately then, E tan 1 should be equal to E tan 2. If a tangential electric field intensity is continuous across the boundary, then tangential D is discontinuous. So D tan 1 divided by epsilon 1 is equal to E tan 1. We know that D is equal to epsilon E. So D tan 1 is equal to epsilon 1 into E tan 1, which is nothing but D tan 1 is by epsilon 1 is equal to E tan 1. Similarly, E tan 2 is equal to D tan 2 divided by epsilon 2. So D tan 1 divided by D tan 2 is equal to epsilon 1 divided by epsilon 2. So the boundary condition on normal components can be obtained by applying the Gauss law. So dn1 del s minus dn2 del s is equal to del q, which is nothing but rho s del s. So dn1 minus dn2 is equal to rho s. So from this dn1 is equal to dn2. So normal component of D is continuous. It follows that D is equal to epsilon E. So dn1 is epsilon 1 into en1. Similarly, dn2 is equal to epsilon 2 into en2. So this epsilon 1 into en1 is equal to epsilon 2 into en2. So and normal E is discontinuous. So boundary condition for perfect dielectric material, we are going to consider the condition for refraction. So refraction of D or E at charge free dielectric interface. So we have two mediums. Epsilon 1 is for medium 1, permittivity of medium 1, and epsilon 2 is the permittivity of medium 2. D1 is the electric flux density of medium 1 and D2 is the electric flux density of medium 2. And we're going to consider the refraction of D, electric flux density or electric field intensity at the charge free dielectric interface. The condition may be combined to show that there is a change in vectors D and E at the surface. So let D1 or E1 make an angle theta 1 with the normal to the surface. Since normal components of D are continuous, dn1 will be equal to d1 cos theta 1, which is equal to d2 cos theta 2, which is equal to dn2. So dn1 is equal to dn2. So dn1 is d1 cos theta 1 and dn2 is equal to d2 cos theta 2. Since d1 and dn2 are same, equal, so we can equate these two terms. So dn1 is equal to d1 cos theta 1, which is equal to d2 cos theta 2, which is equal to dn2. The ratio of tangential components is given by d tan 1 divided by d tan 2 is equal to d1 sin theta 1 divided by d2 sin theta 2, which is equal to epsilon 1 by epsilon 2. So epsilon 2 into d1 sin theta 1 will be equal to epsilon 1 into d2 sin theta 2. So the division of quantities above equation gives tan theta 1 divided by tan theta 2 is equal to epsilon 1 divided by epsilon 2. So direction of E on each side of boundary is identical with the direction of D because D is equal to epsilon into E. So magnitude of D in region 2 is given by D2 is equal to D1 into square root of cos square theta plus epsilon 2 divided by epsilon 1 whole square sin square theta 1. And magnitude of E2 is equal to E1 into sin square theta 1 plus epsilon 1 divided by epsilon 2 whole square into cos square theta 2. So that's all about the boundary conditions. Condition that is prevailed at the boundary when two dielectric material is considered. Thank you.